This is our last part in our 3-part series on magnetism. In this set of notes, we're going to discuss generators and transformers. In the past 2 set of notes, we've talked about how electricity and magnetism are related, but we mainly focused on magnetism because we haven't studied magnetism before. In this set of notes, we're going to put the 2 concepts together and talk about how electricity and magnetism work together to power our very electrical dependent world. Generating electric current. We know that electric current makes a magnetic field, and we know that a magnetic field creates electrical current. This we've known already. You've seen how this works. What we haven't known is this new name, electromagnetic induction. This is the process of generating or creating a current by moving an electrical conductor relative to a magnetic field. So electrical conductor normally means wires near a magnet. This process is called Faraday's law. We discussed this in our last set of notes. Michael Faraday is the name of the scientist who discovered this, and Faraday's law says that voltage is created in a conductor by changing the magnetic field. He did a simulation on this. We use this process to create electricity, a device that converts mechanical energy into electrical energy by rotating a coil of wire in a magnetic field is a generator. Remember that mechanical energy means motion. So we create electrical energy by spinning a coil of wire in between a magnet. There's 2 types of generators, AC generators and DC generators. AC generators produce alternating current. Remember, AC is alternating. This type is used by power plants. If you can think back to that electricity unit, you know that alternating has 2 directions. This coil is going to go back and forth. We're going to move the bar magnet in and out, creating 2 directions of current. This is the type that's used by power plants. Remember, it's this type that is in your buildings. When you plug your phone to charge into an outlet, what's running into the outlet is alternating current. That's why power plants produce it. The second type is DC generators. DC generators produces a direct current. And these are the small generators used in power outages. If you lose power and you have a generator at your house, most likely it's creating direct current. And direct current is one direction. Alternating is switched back and forth. Direct current is one direction. And remember, this is anything that's battery powered. So things like your cell phone or flashlight, small devices, are run on direct current. You actually have to take alternating current in the outlet and convert it over to direct current to power your phone. That's why you have the little box that you plug it into. That little box that has the outlet plug in it, you know, this thing with the outlet and then the cord runs. This is actually a converter between AC to DC. Alright, transformers. We need to take the power created in a power plant and get it to a building, a school, a home, wherever it's going. If you pay attention, if you look around, you're going to see these things in your neighborhood or somewhere close. This is a transformer. Sometimes you might have lost power and heard that your transformer down the street blew or the transformer was struck by lightning. These transformers are very important in how we get electricity from a power plant to a building. What a transformer does is it increases or decreases voltage and current. We do this by two coils. Okay? We have one coil and a magnet and another coil. And the number of coils is going to be different for each. A step-up transformer increases voltage and decreases current. The primary coil is going to have 100 turns, and the secondary coil is going to have 400 turns. So we have, in the first one, less than the second one. We go from less to more. We use a step-up transformer because over a long distance of wire, current is lost. We'd be losing power. It's not efficient. But if we decrease the current and increase the voltage, we're able to transport electricity without losing power. In a step-down transformer, it's the exact opposite. We decrease the voltage and increase the current. The primary coil is going to have more. Is going to have 400 coils. And the secondary is going to have less, only 100 coils. Notice how these two numbers switched. We go from primary, where there's a lot, to less. To get power from a power plant to your house or a building, we're going to first start with the power plant. Okay? You're going to really see how bad I draw here. This is our power plant. Remember, the power plant is an example of a generator. From the power plant, we need to increase the voltage. So we're going to go to a step-up transformer. And here, we're going to increase voltage and decrease current. Next, we're going to travel over power lines. A very long distance, or however long we need to travel. This is our power lines. Those high voltage wires, they say do not touch, high voltage. Right? It's because a step-up transformer increased the voltage. And then we get to a step-down transformer. Because now we need to decrease the voltage. You do not want high voltage going into your house. Remember, this decreases voltage and increases current. And finally, we're able to go into your house, building, wherever needs the electricity. So hopefully at this point you're going to be able to say the difference between a generator and a transformer, and how electricity and magnetism work together to allow us to run our buildings, our schools, anything that has electricity. This path of moving from the generator to a power plant through to your home, school, whatever building we're powering with electricity, knowing the steps along the way is going to be very important for your quiz on Friday. So make sure you understand this process and what happens at each process.